All right, today we're going to look at 2.7 precise definition of limits. So it describes that in previous sections we've used words such as sufficiently close, arbitrarily large, and they need clarification. And so in this section we're going to be moving to a more precise definition. And so as you go through and read, it is explaining that when we get close, we can use that value of the limit, and when we say close, we're actually looking at the distance between two different y values. So the limit definition says we're observing the distance between f of x, which is one y value, and L, the limit, which is a different y value. And if we look at the absolute value of the difference between f of x minus L, the distance between those two getting really small, and x and a, which are two different x values. X is the x coordinate and a would be the x value that we are approaching. If we look at the distance between those should also be getting closer, or the distance should be getting smaller as the distance between the two y values are getting smaller. And so therefore they can write the limit of f of x as x goes to a is equal to L if we can make the distance between f of x and L arbitrarily small, so absolute value of that really small, for any distinct value x, some x value distinct from x, which is a, where x minus a is also sufficiently small. And so here we go through showing you we can use any positive values, 0.01, 0.001, and we can find a corresponding delta that would match and make that same, that x minus a would stay within the range of delta. And they won't always be equal to the same. Sometimes they can be, but sometimes they'll be different. And what that means is, if you look at this example here, if we trap y within 1, so we want this value to be less than 1. So when you think about absolute value, you're basically adding and subtracting 1 from that middle number, making a symmetric interval. That would correspond to x coordinates that would also trap x within a certain range, and in this case it happens to be 2. And so you see several different examples showing you the relationship between epsilon and delta. Okay, so this kind of goes over again, like how can we figure this out every time no matter what. And so this is going through the process that if we pick a certain epsilon and f of x minus L is going to be less than epsilon, we can figure out the relationship that delta needs to match so that x minus a is less than delta. And this goes more into the precise definition. It also goes over just here's the limit of a function again, and the definition for f of x minus L being less than epsilon when x minus a is less than delta. Sometimes we get the example where it's not symmetric. So in this case, we want to make symmetric intervals. That makes everything nicer. However, sometimes you don't get a symmetric interval. So if you look at this almost like a piecewise function, you got two different slopes happening. And so whenever we pick an epsilon and then we trace that back to find delta, in this example, we get a different open interval. So they're showing you 1 to 6 when we're approaching 2, I believe in this first example for A. So as we're approaching 2 in the x coordinate, the y is approaching 3. And we made a symmetric interval about y. So we went up 2 and subtracted 2. So we have a symmetric interval 1 to 3 is 2 long on each side. But when you trace that back to the x coordinate, this goes from 1 in the domain all the way to 6 when 2 is a middle number. So this is not a symmetric interval. So in order to make it symmetric, it's going through and telling us we want to use the smaller of the positive number, or maybe if it was negative, we use the smaller of the absolute value of those two negative numbers, the one that makes the distance the smallest. And so then they can make a symmetric interval so that we always stay within the epsilon delta definition. The rest of the section goes over some proofs, so it gives you a little bit deeper understanding of the epsilon delta definition. And so they're just going through improving how we know this works and showing you the relationship that would exist between epsilon and delta. You get to justify it using the triangle inequality. Also, it goes over infinite limits. So you got two-sided. I think it also talks about one-sided infinite limits and limits at infinity. So overall, we're going to be just using the precise definition. And with that, we're going to jump into MyMathLab and do a few examples.